So we are not going into much more details, the polarizability. Now, as I said that this is actually an approximation, in the sense that if the field strengths are low enough, then we can think that this induced dipole moment actually depends linearly on the electric field. But more generally, the induced dipole moment can also have nonlinear dependence, and we can actually write the induced dipole moment as sum of terms, where actually the first term is the linear term, which is basically known as polarizability, and the second term and the third term and so on, we write those constants as hyperpolarizabilities. So, for example, this beta is known as the first hyperpolarizability. The name is basically self-explanatory, because alpha was the polarizability. So, beta is the first hyperpolarizability. And similarly, gamma will be termed as the second hyperpolarizability, and so on. Now, you can see that mu induced is a vector. So, it will have always three components, mu x, mu y, and mu z. Now, if I have E square here, so then actually I will have Ex, Ui, Ez, and I will have basically twice of that. And then you can think that the dimension of beta will not be just 3 by 3 matrix. So, it will be a higher order matrix, and in general we call those as tensors. So, we cannot actually go through all these details of the tensor algebra, how basically the dimension of the beta or the gamma or the higher order hyperpolarizabilities basically has the dimension, but we'll more or less restrict our discussion on the induced dipole moment, which actually depends only up to the first term, and where actually we are ignoring all the higher order dependence on the electric field. Now, this higher order dependence will of course depend when will of course become important when the electric field strength is very high. For example, here so far we have been discussing about the application of the electric field as a static electric field. So far we have discussed this application of the electric field, external electric field, as a static electric field, but we could also do it by applying light, because light has a electric field as well as a magnetic field, of course, which are oscillating in time and in space, because light is a propagating wave. But when light is applied on light is basically shed on atoms and molecules, the physics that happens is very much the same, that the electron and are basically slashed around the nuclei from their equilibrium position, and then we create a dipole, but this dipole also oscillates because the electric field of light also oscillates, and there actually make an approximation which is known as the induced dipole approximation, because we only consider the electric field of the light to affect the dipole moment, and there we talk about the creation of the dipole moment or the induced dipole moment as electric dipole moment. We do not consider the magnetic field of the light in general, and there we can actually have a very intense light source. For example, if we use lasers and focus it very tightly, then actually the electric field in the focus at the focus will be very, very high, and then all these higher order terms which are dependent on E square and E cube will be non-negligible, and then we have to consider those terms, and that gives rise to an entirely fascinating new field, which is extremely fascinating, which is known as nonlinear optics. Basically, where actually you can see very fascinating example, like we send red light through a crystal and then we get a blue light at the output, and how basically the energies of the two photons gets added up and a new photon is thrown to the output, and those kind of experiments are routinely done with lasers. Now, coming back to the polarizability or the linear polarizability, often we write the polarizability in terms of the polarizability volume, which is basically a reduced way of writing it. We define the entire polarizability by 4 pi epsilon 0, where epsilon 0 is basically the permittivity of vacuum. So I hope that you have already learned all these basics of electrostatics in your high school physics, and you know that in that case we can just tell this alpha prime as the polarizability volume. Why volume? Because actually it has a dimension of volume. Now why it will take a dimension of volume is also like we can understand it from a very different perspective. So if we want to write the quantum mechanical way of what is the polarizability expression using perturbation theory, second order perturbation theory, I am just writing the expression for you, and then we have basically we have something like mu. Let's say we are talking about the z component of the dipole moment, and then we have mu z, and we have say some zero state. I will come back to it. What are the about the notation here. So here what I am saying here, I have two energy levels which I have noted here, and so these energy levels are basically the unperturbed energy levels, and of two this corresponds to the energies of two unperturbed energy levels E0 and En, and you can think that this to an approximation represents the homo-lumo energy levels in a polyatomic molecule. Now you can make approximations, so like in the sense that this thing you can think about roughly as the energy difference of the homo-lumo in the molecule. So I am just replacing it as delta E, and the mu you can think about some charge distribution times the distance. So overall this alpha you can approximate to be something like so this charge distribution, if you think that each atom has some charge of which is fundamental electronic charge, which I am writing as E, so it is E square R squared divided by delta E. Now as you can see that if I reduce the delta E, or if I actually have the less separation between HOMO and LUMO, then actually I will have more polarizability, as well as if we have more R square, which means actually if we have more of the R or the distance between the dipoles, which actually directly connects to their volume, I will have more and more polarizability. But to get to know how basically it is, why we are calling it as a polarizability volume, let's do one more step. Now how do you calculate the delta E? Now the delta E, as you can think, we can actually say that this delta E is basically as if there is a positive charge and I am moving the positive charge over a distance say R, and then we can think that basically connects to the excitation energy from say HOMO to LUMO, and we can think that again this is a very crude description, that the delta E you can actually approximate as E square divided by 4 pi epsilon 0 R. So this is this basically tells that if I have a unit positive charge at a location R from some origin, and then I am removing that unit positive charge from that location to infinity, so this will be the energy required to do that. So this is by definition of the electrical potential energy that is stored if I keep the positive charge, or if that is basically spent if I want to move that positive charge to infinity. Now we can actually replace this value of delta E in this equation, and what we find here is that I will have alpha will be something like 2 times 4 pi epsilon 0 into, I have one R here and one R here, so I will have R cube. So if I, by definition, alpha prime is nothing but alpha divided by 4 pi epsilon 0, and if we ignore the factor of 2 here, so you see that alpha prime is roughly equal to R cube, which is basically roughly the volume. So that's why you call it as a polarizability volume. But again, this description all of you may not be very familiar with. You can actually look at the quantum mechanics textbook, and if you know a little bit about perturbation theory, or basically the second order perturbation theory. This is actually first order because here actually the denominator, as you can see, is basically n minus E0. So basically the first order perturbation theory tells you how the energy level shifts when an external field is applied. The second order perturbation theory tells you what happens when I couple the two energy levels. So this actually directly comes from the first order perturbation theory. Now the next thing is that this polarization which we talked about, it actually depends on the frequency of the external field, because here we are applying an external electric field and we are creating polarization or basically dipole moment. We have not actually defined the term polarization. The term polarization is basically tells you what it's called a macroscopic polarization, or simply as polarization. So suppose when you do this experiment on say a gas or a liquid where actually we have some molecules which has a very high alpha, which means actually if I apply an external electric field which can be static or which can be a time varying electric field as we see with light, then actually I create a static dipole or a time varying dipole, which is an electric dipole in this case. And it depends, the strength of the dipole depends on the magnitude of the alpha or the polarizability. So basically this polarizability tells you how with what ease we can actually distort the electron cloud so that we can actually create a dipole moment momentarily as long as the electric field is present. If we actually remove the electric field or if we can turn off the light, then actually there is no polarizability because it just stays as long as the light is there. So that's why it is an induced dipole moment, and then we can actually add up all these dipole moments of very, very small molecules, and then we can think about creating a macroscopic polarization. Now on average you can think that if I am applying a particular electric field in a particular direction, more or less there will be some preferential orientation of this molecular or the tiny electric dipoles along this direction, which can actually give you net polarizability and a macroscopic polarizability along a particular direction, and that we talk about as some mu times the number density, and this mu now is an average mu which you can think of, and times the number density. So this is basically known as the macroscopic polarization. So macroscopic polarization is directly connected to the mu induced. Usually the mu induced is described in the molecular context, and when you talk about in the atomic or molecular context, and when you talk about a macroscopic system, then actually we have to take the average mu and then multiply it by the number density of the molecules. Then basically this P, or the definition of P, is something like that. It is basically the macroscopic dipole moment per unit volume, because number density is nothing but the number of atoms or molecules per unit volume. So P is nothing but the dipole moment per unit volume. So we can write it as it is nothing but the macroscopic or the measurable dipole moment that you can measure per unit volume. So we'll now try to understand what is the value of this mu average, because when you apply an external electric field, you have to understand that what is the mu average. Now you can think that in case the way we have written this equation of mu induced, that it depends on the electric field, the total mu will be something like the mu permanent, which we talked at the very beginning. The molecules may have a permanent dipole moment, and then the induced dipole moment. Now you can think, if I have water molecules, now water molecules already have permanent dipole moments, and if I do not apply any electric field, then it will have each molecule will possess only the permanent dipole moment. But in a macroscopic system, all these dipole moments, in the absence of any external field, will be randomly oriented. So what we will have is that we'll have a net zero dipole moment or net zero polarization in the system. But when we apply an external electric field, then all these permanent dipoles will try to orient themselves along the field, as well as the field will also induce some induced dipole moment. So the total dipole moment, which is basically contributed as a permanent dipole moment plus the induced dipole moment in the presence of the field, that dipole will try to orient itself along the field. So we will have a distribution of dipole moment along the field, and that will give rise to a macroscopic polarization in the system that we are now going to discuss. So before we go to the derivation of the average value of this induced dipole moment, basically it's the orientational average of the induced dipole moment, let us also discuss some other aspects of the induced dipole moment when it is created as an application of the external electric field. Now what we are going to ask is basically what is the energy which is required to what is the potential energy of a dipole which is at an angle let us say theta with respect to the applied electric field. So what we have to do here is basically, suppose I have a dipole, and again let us take the charges as plus q and minus q, and suppose we are applying an external electric field which can be time dependent also, then the sign of the dipole will change with time because it will follow the electric field. And suppose you have a positive end or a negative end here and a positive end here, something like that. So then what you can think that the dipole is now tilted like this, it's at an arbitrary angle, and we can think that this angle is basically theta. And then what we are having here is that we are actually having force on the dipole on the two ends. So basically we are creating torque on the dipole, and as before I was using green for the positive side and pink for the negative side. So we have been created a force along each charges on each charges of the dipole. Now what is this magnitude of this force? Now again as before let us think that the distance between the charges that create this dipole is r, and the electric field is now applied from the positive side is this and negative side is this. So the electric field is applied something like this, and the question we are asking, what is the force that is acting on the dipole, on the charges first. Now the force acting on this charge, for example the plus charge, which will be in this direction, and the force which is acting on the negative charge of the dipole, negative end of the dipole we should say, which is acting in this direction. Now this magnitude of the force will be basically the charge times the field, which is basically if I write the charge as q and electric field as E, which is the strength of the field. The question is what is the torque acting on this particular dipole. So then we talk about the lever arm of the dipole, and remember that the lever arm is basically we have to take a projection of this distance between the dipole, half of that towards the direction. So in this case it will be r by 2 sine theta. So the overall torque which will be acting on the dipole, which will be basically addition of these two forces, and then it will be force times 2 times the dimension of this lever arm, basically 2 times the length of the lever arm. So then the force is nothing but q into E, and this lever arm into 2 times is basically r sine theta. So this is not I should not write it as a cross, because I am just writing it as a simple multiplication. So it is basically q E r sine theta, and q r already we know that this is mu. So it is basically mu E into sine theta, which is nothing but, in the vector notation, mu is a vector which is a dipole moment, and E is also a vector which is the applied electric field. So the torque is nothing but actually the vector product between mu and E. So so mu E sine theta is the magnitude of the torque. So the torque itself is mu cross E. Now the question is what will be the energy of the dipole. Now you can think that I am basically rotating the dipole from an angle which was initially at 0 degree with respect to the electric field, which means actually which was at some angle 0 degree, and then I am actually rotating it to an angle theta, so that the dipole has now a particular orientation, and due to this rotation I am doing some work, and that work done will be basically stored as the potential energy of the system, which is basically the potential energy of the dipole itself. So this work done, in order to calculate, we have to basically talk about like work done if I have a linear motion, it will be force into displacement. And now if we are applying a torque, it will be nothing but the force equivalent of rotational motion, which is torque, okay, times instead of displacement it will be the rotational angle. So it will be tau d theta, and going from say 0 to we'll have to a particular angle, let's say theta, and then we can actually use d theta prime, because theta prime is the variable. Now what is tau? Already we talked about the magnitude of tau. Okay, so tau is basically the magnitude of the torque applied, so that is mu e sin theta d theta. So we are using theta prime here from 0 to theta. Now derivation of cos theta is basically minus sin theta, so integration of minus sin theta is cos theta. So the integrand is nothing but mu e, again the e is independent of theta, mu and e. So we will have the integrand as minus cos theta, and which is evaluated between the limits 0 and theta. So it will be minus mu e cos theta, and cos theta evaluated between 0 and theta. So it is minus mu e. So when theta, the upper limit is theta, I will have cos theta. We can write it as theta prime, and then when the lower limit is 0, cos theta is 1. So this value of the integrand, the work done, is nothing but mu e into 1 minus cos theta. So that is the work done, and this work done will be stored as the potential energy of the system. Now we have to define a zero of potential energy. Now the zero of potential energy, you can think that when the angle between this dipole which is created and the external field is 90 degree, then you can think that that is basically an position where basically this dipole and the field are not interacting, because it is basically the force acting on the dipole due to the field will be 0, because cosine 90 is 0. So then we can think that in that from that perspective we can choose u equal to 0, or the zero of potential, when theta is 90 degree, or basically pi by 2, and that will give us that u 0, or basically the zero of the energy will actually correspond to basically again u will be a constant, and that constant we are taking it to be 0. So we better actually write it as u0. So the u0 will be nothing but mu e 1 minus cos theta when theta is 90 degrees. So it is 1 minus 0. So it is nothing but mu e. So we are taking that to be u. So what we said is that this work done will be stored as basically the potential energy of the system. So this is nothing but the total potential energy u, and we just saw that mu e is nothing but the potential energy, or the zero of potential, which we can choose. So then we just define that u is nothing but, as you can see here, mu e minus mu e cos theta, so which is basically u0 minus mu e cos theta. So if we just always plot the potential energy with respect to a zero of potential, which we chose to be the potential u0 to be 0, so that value will be minus mu e cos theta. So which is nothing but minus in a vectorial notation, which is nothing but minus mu dot E. So it is basically the dot product of the electric field with the dipole moment. Again, that dipole moment can be permanent or the dipole moment can be induced. Even the dipole moment is permanent. When the electric field is applied, there can be an induced part also in addition to the permanent, and for those atoms or molecules which do not have a permanent dipole moment, it is all induced. So we will get a definition of the energy stored with respect to a zero potential. Again, the zero potential was chosen as the configuration where the dipole is basically oriented perpendicular to the applied electric field as minus mu dot E. Now this expression probably you have seen when we talk about basically transition between one energy level to another energy level. Whatever is the transition, it can be an electronic energy level, then we apply an electromagnetic energy at visible frequencies or ultraviolet frequencies. So something like we have already seen, and then we talk about a mu, which is also an induced dipole moment, because when you apply light, as we said, that light actually has an electric field which is oscillating in time. So you have an oscillating induced dipole moment. But you can actually think all this spectroscopic transition, or you can actually explain all this spectroscopic transition which we initially study in our quantum mechanics or spectroscopy class from a very much quantum mechanical point of view, has a classical picture where basically we are again in quantum mechanics using second order perturbation theory, you learn that we are coupling the two states. But here what we are saying here is that it has a classical thing, as if I created an induced dipole in the system, and this induced dipole, which is known more specifically as the transition dipole, and this transition dipole moment is trying to align with the field, and that alignment is basically stored as the energy, as we said, and this is basically the energy for the transition. And this is known as the transition moment integral, and when you write the transition moment integral spectroscopically, and we write basically an operator which acts between the two states. Suppose I have the state says something like that, 1 and 2, and the wave functions are say psi 2 and psi 1. So I am coupling it so that I will have a transition from state 1 to state 2, and then we write in the wave function way that I have a psi 1 wave function, then I have an operator which is the transition moment operator, which is coupling the psi 1 with psi 2, and that operator we write as minus basically mu e. The minus sign we can drop it for the time being because we take always the magnitude. So here we wrote actually the operator rotation, mu operator and e operator, and then we write psi 2 here and psi 2 star here, and then we integrate over the entire volume. So this is basically the transition moment integral. Now originally transition moment integral also have a square because actually it is the intensity that matters. So you have to think about this interaction, the electric field interaction twice, because electric field when it acts twice, basically it acts like first the field interacts and then its complex conjugate interacts, which is equivalent to interaction of a photon. Let's not go into the details of that. And then the point here I wanted to make is that the operator form is the same as the classical form. So it is mu dot E only. So we have an exact analogy with quantum mechanics. Actually quantum mechanical transition moment integral operator are actually borrowed from classical physics, where we see that we are creating a dipole, and it's an electric dipole which is basically created, and the electric field of light is causing this transition. So by logic we will have the operator of the form of mu dot E, which we just explained.